Hey everyone, welcome back to our three-part series on the reactions of Chapter 7. So this is going to be the very last video in this series. We have already talked about E2, E1, but now we're going to talk about dehydration. Okay, so dehydration is going to be a little bit different than some of the other ones that we've seen. So dehydration of alcohols. All right, so we know what dehydration means, right? It means we're low on water or something like that, right? So that's what's happening with dehydration of alcohols. The alcohol is losing water. Water is leaving, okay? So there's a couple things that we need to know about this. There's not as many as E1 and E2 as far as the bullet point lists that I'm going to write, but there's a couple things that I want to write here, okay? So as far as dehydration of alcohols goes, um, we use an acid, right? So we use acids such as H2SO4 and H3PO4. So H2SO4, sulfuric acid, H3PO4, phosphoric acid, those types of things. Okay, so those are the two kinds of acids that we use. There's others, but those are the two that we're kind of worried about for this class. Another thing is that this can be done with 1 degree, 2 degree, 3 degree, whatever kind of alcohol, but the mechanism depends. So 2 degree and 3 degree alcohols follow E1, and then 1 degree alcohols follow E2. And we'll see that. We'll see that a little bit later. Another thing is that this is a two-step reaction. Okay, so there's a carbocation intermediate. So rearrangements are possible. Okay, rearrangements are possible. Another thing to say is that for the alkene, it forms E and Z products. And also it follows Zaitsev's rule. So that means that the most substituted alkene is going to be our major product. All right. So it follows the Zaitsev rule. All right. So let's do something really quick. Let's look at an example here. So this one's not going to have a shift or anything. It's just going to be a simple one. But if we take a look at this one here, so we're just going to put this through, say, 20% H2SO4. So we put the acid on top, and then usually on bottom we put heat. Okay, so we usually heat it in acid. And then this is just going to give me an alkene, right? So it's going to give me the most substituted alkene. There it is, right? That's my alkene. So now if we want to look at the mechanism for this, so this is a 2 degree alcohol, right? So this is a 2 degree alcohol, so this is going to follow an E1 type mechanism. So what that means is that the leaving group's going to leave first and form a carbocation, and then I'm going to form my alkene, okay? So, but before we do that, there's something we need to do. So for H2SO4, right, the strongest acid that can exist in water is hydronium. So H2SO4 does not exist in solution. It's going to protonate water to form hydronium. So we have to write that every time. So anytime I do a dehydration reaction, I'm going to have to write hydronium, which is, or excuse me, not hydronium, sulfuric acid, which looks like this. So it's an OH bonded to an S, double bonded to two O's, which is also bonded to another OH. Okay, and then I'm just going to write my electrons on this as well. So those are all my electrons. And then what can happen is that water can come in and take a hydrogen off. Okay, so if water comes in and takes a hydrogen off, then what I'm going to get is hydronium, H3O plus, and then I also get HSO4 minus. So H2SO4 with one less H. All right. So my hydronium is going to be acting as the acid. So now that we've written this, we had to write this first, then we can write the actual mechanism. So the actual mechanism is going to look something like this. So my alcohol here is going to get protonated by hydronium. So hydronium is an acid, so it's going to act as an acid. And this alcohol is going to be acting as a base. So it's going to, this alcohol acts as a Bronsted base. It's going to take a hydrogen off the hydronium. And then these electrons are going to go onto that oxygen. All right. So then what we get is a protonated alcohol. So this alcohol is protonated. So it has two hydrogens on it now, and it's positively charged. And then we also get water. Okay, we also get water. So O with two H's here, right? That's H2O. This is water. So this is a fantastic leaving group. So what it's going to do is just leave immediately. All right, it's going to leave because it's a great leaving group. Water is very stable by itself, so it's going to want to leave. All right. So once that leaves, then I get my carbocation here, and I also get water. Again, I get another water, right? I'm forming a lot of water out of this. And now I'm going to take a hydrogen so that way the most substituted alkene is formed. All right. So I'm going to take this hydrogen here. And then just like in E1, I take the hydrogen and then the electrons in the bond between the carbon and the hydrogen go there to form a double bond, just like E1, no different than E1. And then I'm going to write my final product up here. My final product is this alkene. Then I also get hydronium. So that is my final product. Okay. And that's what I've written over here. The only other thing that we need to mention is that we do form this product, but we also form this product, okay? So just like this is E and this is Z, right? We form both E and Z products. So these are both major. Because this follows Zaitsev rule, but it forms E and Z as well. So just like E1, this is no different than E1, right? It just so happens to be an alcohol instead of an alkyl halide, right? So we form both E and Z in this reaction. The other thing to mention is that we do form this one. We do form this, but again, just like it would be in E1, this is minor, okay? So these are my two major products. Why? Because these are the Zaitsev products, right? This follows Zaitsev's rule. So the more substituted alkenes are going to be the major products, all right? So this is the minor product. So we're not too worried about that. So if I was going to write the major product, I'd write these two, all right? Okay. So now we're going to look at what happens if we don't have a 2 degree or 3 degree. All right. So this is the mechanism if we have a 2 degree or 3 degree alcohol. If we do not have a 2 degree or 3 degree alcohol, it's going to be slightly different. Okay. So we're going to take a look at that next. So in this case, I'm going to be using a 1 degree alcohol. So earlier I said that 1 degree alcohols, so we'll say 1 degree alcohol mechanism. So 1 degree alcohols do not follow the same mechanism as 2 degree and 3 degree. 1 degree is going to go through an E2 mechanism. Okay. So again, I'm going to be using H2SO4 and heat. And in this case, I'm going to form this alkene. All right, that's the alkene I'm going to form. So let's look at the mechanism for this and see exactly how this forms. So again, the very first thing that I need to do is write out my sulfuric acid. Okay, so I wrote out my sulfuric acid and then my water. And then water is going to act as a base, take a hydrogen off sulfuric acid. So then we get our hydronium. And we also get HSO4 minus. Okay, so now we have hydronium, good to go. So let's take a look at this. The OH is going to do the same thing it did last time in our previous reaction. So it's going to act as a base and take this hydrogen. Those electrons are going to go onto the oxygen. And then we form our protonated alcohol, just like we did last time. Okay, so this isn't anything different necessarily yet. And then we also get water, right? We also get our H2O. Okay. So now, instead of this leaving and then it forming a carbocation and everything, if this left, it would form a primary carbocation. Remember that primary carbocations are not stable, so the molecule is not going to want to form a primary carbocation. So to avoid that, we're going to go through an E2 mechanism instead. So a hydrogen is going to get taken from the adjacent carbon, all right, by another water. So water is going to come in, act as a base, and take a hydrogen. And then these electrons are going to go here. And then just like in E2, if they're going to make a double bond here, something has to leave, right? Or otherwise this carbon's going to have 5 bonds. So I have to make sure that this leaves at the same time. So hydrogen's going to get taken, form a double bond, and this leaves all at the same time. So that means that I get, this is my product, and then I also get hydronium. So this is what happens whenever we have a 1 degree alcohol. Okay. So that's our 1 degree alcohol mechanism. Okay. So it's going to have to follow E2. Now, let's take a look at rearrangements. So earlier I mentioned that rearrangements can happen. So we can have a hydride shift, methyl shift, ring expansion, anything. There's only 2 that I'm going to do in this example. I'm going to do a methyl shift, and I'm also going to do a ring expansion that just so happens to also have a hydride shift in it. So we'll technically get to see all 3, but this is just basically a methyl shift and a ring expansion. Okay. So let's do the methyl shift first. All right. So what we're going to do is this one. Then again, I'm just putting this through H2SO4 and heat. And my major product is going to be this. So then let's take a look at the mechanism. So the mechanism is going to be, again, unfortunately, I have to write out sulfuric acid. And then water. So then this is going to give me hydronium, H3O plus, and HSO4, whoops, HSO4 minus. Okay, so now we made hydronium. And again, this is a 2 degree alcohol, so it's going to go through an E1 mechanism, right? Not E2. So we're going to form a carbocation, and that's why we have our shift, right? That's why we have the shift. Okay, so now let's take a look at this. So this alcohol is going to get protonated. So let me write the hydronium here. So this alcohol is going to act as a base and get protonated by the hydronium. Those electrons are going to go on there. So then we protonate our alcohol. And now this is going to leave. This is an E1 mechanism. And almost forgot to write that we get water. Sorry about that. We also get water. And so now this leaves. So we get a carbocation here, and we have our two methyls, and then we also get water. All right. Okay, so now we can have a methyl shift. So our methyl is going to move there. And then I'm going to write methyl shift here. So then I get this, and then this bottom carbon just lost a bond, so my positive charge is here. So that means I'm going to take a hydrogen from there to form this, right? So water is now going to come in, just like it had been earlier, right? There's no difference now. Water's going to come in, take that hydrogen, that's going to go there, and then that's going to form our double bond. Whoops. It's going to form our double bond, and then we also get, you guessed it, hydronium. We're done. That's it. Okay. So that's what our methyl shift looks like. Okay. Very similar to methyl shifts in SN1, really no different. The mechanism is just very slightly different, but the methyl shift happens exactly the same, right? There's no real difference there. All right. Okay, I'm going to move down slightly here, just so that way we have enough room to talk about our ring expansion. So in this one, we're going to be doing a ring expansion. So I'm going to do a 5-membered ring to a 6-membered ring. So we'll do this. Then again, we're just putting this through sulfuric acid and heating it up. And we'll see what the product is. We'll do the mechanism first, then we'll kind of see what our product is going to be looking like. So hydronium is going to be formed at the very beginning. So we need to write out our sulfuric acid. This is just the step every time. It's monotonous, but it shows where we're getting everything. And that's the importance of the mechanism. We need to show exactly where everything is coming from. Okay, so water, again, is going to act as a base. It's going to take a hydrogen. And then I get my hydronium that I need to do the reaction, and I also get HSO4 minus. Okay, just like I have been doing. All right, and again, this is a 2-degree alcohol, so this is going to go through a E1 mechanism, and it's going to have a carbocation. So that's the whole reason we can have our ring expansion in the first place, right? So now here we go. Very first step, alcohol is going to get protonated by the hydronium. Okay, so our positively charged hydronium is going to come in here, get a hydrogen taken by the alcohol, and then the alcohol is going to become protonated. So now we get our protonated alcohol, and we also get water. So now this follows E1 mechanisms. This is going to leave to form a carbocation. So that means our carbocation is here. Then we also get water, right? Okay, so now I'm gonna number this ring just so we can see what's going on. This isn't necessary, but I think it's easier for us to kind of tell what we're looking at. So 1, 2, 3, 4, 5. So then my carbocation is 6. This is 7. All right, and let me move that 6 over just slightly. This is 6. This is 7. Okay, so now my ring expansion is going to happen. This bond is going to move here to this positively charged carbon. And then, so this is my ring expansion. And so it's going to move there to that positively charged carbon. So then I'm going to write my 6-membered ring, because that's what I'm expanding to, right? This is 1, this is 2, 3, 4, 5, 6. So then 6 is the carbon that had 7 coming off of it. So that means that 7 is going to be down here, all right? And then the bond between 1 and 5 broke, right? My 1 and 5 bond is not there anymore. So that means that 1 has a positive charge on it. 1 lost a bond, 6 gained a bond, right? So that means that 1 has a positive charge on it now. Okay, so this is a 2-degree carbocation. You'll see that I have a methyl group here. I can actually shift a hydrogen to make a 3-degree carbocation, right? So I'm going to do a hydride shift now. Okay, so now I'm going to do a hydride shift. This is pretty common in ring expansions where we'll get double shifts like this. Okay, so now we do our hydride shift, and you know what? I'm gonna go down because we're gonna have to work off of this one. I don't want to be too crowded. So our arrow there, and then we get our hydride shift. So that means that we're going to get a positive charge where that methyl is, right? So we get a positive charge here. And then we can take a hydrogen from here if we like, or from the bottom, right? It doesn't matter where we take the hydrogen from, but I'm going to take a hydrogen from here with the water. Now that we've done the shifts, the mechanism's the same, no difference. So hydrogen gets taken, forms our double bond, and then we get our final product, our 6-membered ring, right? And then we also get, don't want to forget it, hydronium. So we'll write our product up here. That is our product. Okay. So this is what a ring expansion that also has a hydride shift in it looks like, right? So we talked about 2-degree and 3-degree mechanisms for dehydration of alcohols, and then we looked at how there's a difference between 2-degree and 3-degree versus a 1-degree alcohol. And then we also talked about ring expansions, hydride shifts, methyl shifts, all that kind of stuff with these, because they have a carbocation intermediate, so they can undergo all this stuff. Okay, so this is important to know and understand. So I think that I'll leave it here. This is going to be the last video in the Chapter 7 series. We're going to go to Chapter 8 next, which is going to be reactions of alkenes. So Chapter 7 looked at how we make alkenes. Next chapter is going to look at what we do with alkenes. So hopefully you found this helpful. Hopefully all these videos have made your study habits better. And I encourage you to continue to practice problems and keep working on these, because this is all very important stuff. So I appreciate it, and I will see you in Chapter 8.